particles on subatomic scales exhibit a strange behavior in that they can act as a particle or a wave in different situations. We call this wave-particle duality. For our purpose here, we'll just say that particles are able to travel as waves, but when they are measured, they take on particle-like form with a definitive position in space. The wave tells us the probability of finding the particle somewhere in space, but ultimately, when we take a measurement, we'll determine specifically where the particle is. There's a randomness to where we find the particle, and this can be demonstrated by repeating an experiment over and over again. Light exhibits this behavior, since it can be demonstrated to travel like a wave, showing interference patterns, which are inherent to wave-like phenomena. However, light can also be detected as discrete particles, or photons, when measured with photon detectors. Even stranger though, it turns out that not just light exhibits wave-particle duality, but all matter as well. In the diffraction experiment, we can think of the waves as probability waves for a particle. If the ratio of the wavelength to the width of the opening is large, the diffraction wave is spread out at the detector, meaning the particle has a probability to hit the screen over a wider area. In order for the particle to hit the detector over a wider range, it must be moving laterally with more momentum.